SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the applied thermodynamics. So, today we are going to start a new module, that is module 6, and the name of this module is reciprocating air compressors. Under this module we have two lectures. Mainly the first one is the reciprocating compressor, and it will be a single stage compressor, for which we will discuss about thermodynamic analysis and modeling. Then in the next lecture we will have multi-stage compression. So, these two topics will constitute this module 6. Now, on the first lecture, that is the reciprocating compressor analysis and modeling, today we will be dealing with the following segments. First is we will try to introduce pumping machines and positive displacement machines. Under these headings, where this reciprocating compressor is going to fit, and for a simple compressor we will discuss about its construction fixture and working principle. Subsequently, we will do the thermodynamic analysis, that means how much power is required to run these compressors for a given pressure ratio, and what is the conditions for minimum work, means that an ideal reciprocating compressor would be one which will consume minimum work. And finally, we will do some steady flow analysis based on the equations, thermodynamic equations we have studied. So, let me start with this compressor. Under the broad roof of compressors, there are many categories, and we will be only focusing on reciprocating compressors. Now, if you look at the compressors, there are two broad categories. One is positive displacement type, other is dynamic type. And basically, there when you need a continuous flow, we require a dynamic compressors, and here the entire idea philosophy is that the kinetic energy is imparted to the fluid, and this through rotation of impeller or these vanes, and through this process necessary kinetic energy is imparted to the blades, and through these dynamic actions the pressure ratio is obtained. And under this dynamic nature we have centrifugal type, axial flow type, and centrifugal type. Under this heading we have radial flow, mixed flow category. So, these particular applications are mainly these type of compressors are mainly find their applications in aircraft engines, and another way is looking at is the gas turbine engines. So, all this dynamic nature of the compressor we are going to use there. But the other category of compressors where we require very high pressure ratio, that means we also do not require continuous flow type. We require for certain time you run the compressor, store it, and when your work is over you can again store it. So, it is a kind of intermittent flow type. So, such a machines we call this as a positive displacement type. Under this heading we have a reciprocating nature, or you have rotary nature. Reciprocating or rotary, here I mean that reciprocating nature will have a piston and cylinder motions, which is similar to IC engines, where there is a suction and there is a delivery or discharge. So, this motion during the motion of the piston, the air gets compressed, and other end the air gets the high pressure gas gets discharged. And here also we can have a single acting and double acting. So, basically when we have reciprocating type of nature. So, one is suction, other is discharge. So, in a single acting situation there is one suction and one discharge, but in a double acting system, when there is a suction in one side, there will be a discharge in the other side, when discharge when there and vice versa. So, that is why we say single acting and double acting type. Other nature is that there are diaphragm types. So, there is a diaphragm which gives the compressing nature of the fluid. So, it also comes under these things. And other domain of this positive displacement type is a rotary. Here the rotary, I mean it is a it is also an intermediate flow type, but other category is that here we require a nature that this reciprocating nature is replaced with the rotary natures, and accordingly we have different versions: a lobe type, screw type, bend type, liquid piston type, scroll type. So, this is not the part of our segment. So, we will mainly focus on a compressors which is reciprocating nature and mostly single acting, and to some extent we will give some introduction how a double acting reciprocating compressor looks like. The another important aspect for when you deal with these compressors is that pressure and capacity. Pressure and capacity means basically we require the fluid or charge or air that needs to be compressed. So, that means its pressure needs to be high. At the same time, when we are going for high pressure, whether we can have a continuous flow type with very high flow rate, or it can be a constant flow rate, or it is a intermittent flow rate. So, that two parameters normally decides what type of compressor is going to be used. So, in a broad sense, if you try to plot the capacity versus pressure, what happens in a positive displacement compressor type, mainly this reciprocating nature type, we will find that it can cater a wide range of pressures, but at a given capacity. At a given capacity, we cannot have a higher capacity continuously changing the flow capacity, that will cover a continuous thing. But in a dynamic compressor nature type, what we can see is that with varying capacity we can have a fixed pressure. So, we can say maybe for this particular, for this range of capacity we can operate the at same pressure, and with higher capacity the pressure will drop. So, this is the mainly because due to the dynamic nature, or sometimes we call as a rotodynamic compressors. So, this is the very ideal situations that is aircraft or gas turbine engines require. So, under that domain the dynamic compressors are widely used. So, basically we are looking at a positive displacement compressor in this course, and we are mainly reciprocating compressors. So, let me start this compressor with an introduction of what is a pumping machines. So, a pumping machine is a device which converts the mechanical energy held by the device into potential and kinetic energy of the fluid. Through this process, it enables the fluid to flow from a region of low pressure to a high pressure and at a faster rate. The most efficient pumping machine is the one which accomplishes minimum work input for the mechanical work for which it is intended. Now, in the category of pumping machines, and we have fans. Normally, these fans they handle large volume of air at low speeds and up to pressure ratio of 1.2. We have blowers, they handle a small volume flow of air, but at higher speed with a pressure ratio up to 4. Then next version is the compressors. So, they are mostly employed for the pressure ratio above 9 by handling large volume of air at higher speeds. So, this is how we are looking at how we have to deal with the compressors. So, normally fans or blower are the smaller version of the compressors, since they are intended for different pressure ratio and different flow rates. So, names are given accordingly. And other category, and these three are mainly for gases, but when you deal with liquids, they also perform similar operations, and we call this as pumps. So, these pumps you might have seen this in our turbo machines fluid mechanics course. The pumps we have centrifugal pumps, we have axial flow pump, we have reciprocating pumps for the applications, but our main target will be on compressors. And now we will give, there are two broad categories of pumping machine, one is reciprocating type, other is rotary type. So, if you can broadly see this figure, that there is an inlet, there is an outlet. So, what we can see is that during the suction stroke, the in a reciprocating compressors, the air gets into the cylinder and it gets compressed, and finally, there is a outlet in which gas is discharged. And similar thing which is attained through the rotary nature of another version of this particular compressors, where we have guide vanes. So, basically rotary means there is a motor or shaft that rotates, and there are guide vanes, and these guide vanes allows the controlled inlet of air or gas, and it goes out in another outlet. So, basically both are doing the same version. One version is achieved through the reciprocating nature of the piston, other version is achieved rotation of the shaft. The reciprocating compress types have characteristics handling low mass flow rates, but with a higher pressure ratio, and rotary types have higher mass flow rate, but at lower pressure ratio. Reciprocating compressors are pulsating in action, that limits the rate of which it can be delivered, but rotary motions have continuous action. Rotary compressors are smaller in size for a given flow rate, lighter in weight, and mechanically simple than the reciprocating counterparts. The reciprocating compressors operate cyclic or pulsating manner such that properties at the inlet and outlet are the average values taken over the cycle, and the boundary of the control volume is chosen such that the thermodynamic states are constant, that means positions are remote from the pulsating disturbance. So, we will discuss more how we are going to deal with the analysis, but in other hand the rotary compressors find suitable in low pressure applications, while for high pressure requirement up to 500 bar or reciprocating compressor are preferred. And irrespective of what type of compressors we have, normally the compressor deal with single stage and multi stage compression with air and water as the cooling medium. The another way of classifying this pumping machine is a positive displacement and rotodynamics displacements, which I have already mentioned. So, if you can see this kind of a graphical or construction picture of a positive machines and a rotodynamic machines, what you can see in a positive displacement machines, we have a piston cylinder, we have suction, and we have discharge. So, we will discuss more details on this. So, what happens, the reciprocating motion of the pistons allows the air to be compressed, and finally, we get the desired pressure at the discharge end. But on the other hand, the rotodynamic type machines, we have rotating impeller which has fixed blades, and there is a suction. When the fluid gets sucked in, the rotating action of this impeller fixed bands imparts kinetic energy to the fluid, and when this kinetic energy again passes through the stationary diffuser plates, which are fixed at the other periphery outside this impeller. So, as a result, what we will have, discharge or flow that comes out through this control flow that comes out through this diffuser nature of this passage, and these are what we call as guide vanes. And finally, the overall discharge, that flow rate that goes out of the. So, this rotodynamic machine is a non-positive displacement machines, and more details on this we will find in aircraft propulsion topics, or you can also find similar topics. We can find centrifugal pump suction, where water is used, which we have studied in the fluid mechanics topics. But in our applied thermodynamics case, we will only deal with the compressor, since we are dealing with air, and we will mainly focus on the positive displacement type machines, that is reciprocating compressors. The other important essential features of a positive displacement machine is that fluid is prevented by the solid boundary from flowing back in the direction of pressure gradient. The reciprocating machines are regarded as the open systems, being steadily supplied with working fluid and transferring work or heat between the fluid and its surroundings at uniform rate. We will deal this thermodynamic modeling for this particular segment. Nevertheless, the internal processes are intermittent. The comparatively low rate at which the machines of reasonable size can handle the working fluid. Now, let me come to the construction features of a reciprocating compressors. So, looking at the figure, what we have seen is that we have a cylinder which is housing a piston. So, this we can see, call this as a piston, and we have cylinder, and this piston is connected to a connecting rod separately. Now, what happens? The atmospheric air enters through these induction systems or induction mechanism, and there is a valve, and when the during the suction stroke, that means the piston moves outward, that is suction. So, during the suction stroke, the intake valve opens. So, the induction of air into the cylinder starts, and the cylinder is filled with the gas. Now, once, and the piston has two extreme limits, one is the dead center, and in IC Indian terminology this we call as a TDC or BDC, but here we will not use the word TDC and BDC, but we will put these two limits in which the piston moves, and that limit we call this as a stroke volume, and this is the bottom limit and this is the top limit. And the entire gas which gets sucked into this cylinder, it can go up to the piston position when it is in the top locations. Now, when the compression stroke starts, so the piston moves backward. So, we call this as a compression stroke, and this during this compression stroke, the entire gas squeezed in a very small volume, and that we call as clearance volume. That means, piston can go up to the upper limit, that is bottom limit, and entire gas that gets squeezed in a very small volume, we call this as a clearance volume. Now, once the compression is over, then we can these valves can open, the delivery valve can open, and delivery will start. Now, what happens when this compression is done, then what happens? The temperature also increases. So, it is likely that the components gets heated. So, to get rid of this heating process, we have water jackets all around, everywhere around the piston as well as around the delivery and suction locations. So, as a result, we can provide necessary cooling, so that just to protect the components. So, this is how the basic operation of a reciprocating compressors, that involves the basic pistons, cylinder arrangement, connecting rod and crank, and this crank is here. That means, in which the piston is connected to the connecting rod. So, there is a clearance volume which I have already mentioned, that towards the dead center of the cylinder, so that piston does not touch the cylinder face, that is the first requirement. This cycle takes one revolution of the crankshaft, and it can be shown as a indicator diagram. The word indicator diagram in thermodynamic sense, we call this as a pressure volume diagram. And here we will talk about the working fluid, which is a perfect gas, and mostly we will talk about air. And in our day to day life, reciprocating air compressors are very common. and there are also spring loaded valves. These valves are employed in the compressors that are designed for automotive action, which means that with a small pressure difference, rapid closing and lifting of the valve is possible for required air flow rate into the cylinders. So, ideally speaking, they require automotive actions that the valve should open and close. So, this is a automotive actions, and this automotive action has to be performed at synchronized manner. And there is a process, there is a issue called as a lifting of valves. So, valve gets lifted, again that gets closed. So, this process, continuous process, is normally controlled through cam mechanisms. So, which is typically similar to IC engine components. Now, let us see the thermodynamic nature or analysis for this reciprocating action of a gas in a compressor, and this shows that there is a schematic representations which shows that the location of piston in any arbitrary positions, and what we have seen is that we have two pressure ratios, that means one side we need air to get sucked in. So, we say the suction pressure, or typically where this machine is installed we call this as atmospheric pressure, and P2 is the pressure that the in the delivery side we require. So, it is a delivery pressures, and this compression process is given a thermodynamic equations what is called as PV to the power n is equal to constants. So, if you recall that our PV to the power n is equal to constant, it is a polytropic equation, and where for different values of m's n or exponent we can define these thermodynamic processes, whether it is a isothermal process or an isentropic process, or in a simple compression process we write it as a reciprocating compressor, we write it as a PV to the power n is equal to constant. And we will discuss in the later part what is the importance of n, why we cannot have n is equal to gamma or n is equal to 1, all this, why you cannot have isothermal or adiabatic or any isentropic processes, but what value of n is best suited for a compressing action. So, what happens is that initially it is assumed that the clearance volume is negligible for this cylinder. So, in this particular figure we have assumed that there is no clearance volume. So, as if that piston exactly reaches this end of this dead end of this cylinder, and again after the compressor and again comes back from that. So, the line dA, so if you look at this particular diagram in a PV plot, the line dA represents the induction stroke, that is the mass in the cylinder increases from 0 to d. So, from 0 to d the mass in the cylinder increases to the required amount to fill the at A. That means, at A entire mass which is supposed to be compressed gets inducted at point A till the point A. So, that means, at point A the induction commences, that means, we require only this many mass or charge that needs to be compressed. So, once the induction commences, when the pressure difference across the valve is sufficient to open it. So, the process dA is a constant pressure for which there is no heat exchange to the surrounding, and temperature remains constant T1 at that situation. So, now we will see that line ABC there. So, from A we have B and C. So, it represents the compression and delivery stroke. So, as the piston begins to return stroke, the pressure in the cylinder rises. That means, once the induction is over, from point A the piston moves back. So, that we call as compression. And how long it goes? It goes up to point B. So, this compression is given by this equation. So, as the piston begins to return stroke, pressure in the cylinder rises and closes the inlet valve. How long pressure keeps on rising? It goes rising till the point B until the pressure is reached at which the delivery valve is opens. When there is a delivery valve opens, that means its value is decided, that means till we reach this desired pressure P2, the delivery valve opens, and its value is decided by the valve and the pressure in the receiver. So, delivery means it goes to another container or receiver where it needs to be stored. The delivery takes place in the line BC. So, as long as till this point at this temperature, the delivery stroke starts from B to C. So, the cycle is repeated at this end of the stroke. The value of delivery temperature depends on the compression law of compression between state A and B, which in turn depends on the heat exchange with the surrounding during this process. Now, from this we can frame a general thermodynamic equations, how much mass gets inducted and what is this thermodynamic processes and how much work is required to compress certain slug of mass. So, we will now work on this particular PV diagram, because the pressure volume diagram is very basics, and ultimately after explaining this process A to B, actual process from A to B and C, but a simplified version of this is writing a simple equation PV pressure volume diagrams, where the initial state is 1 and final state is 2, and through this initial and final state this process happens A to B. So, in the end, so if you can summarize this particular entire events, we can summarize in just one diagram, where the thermodynamic state of a given gas gets changed from the state 1 to state 2 by following the law of compressions Pv to the power n is equal to constant. Now, let us recall our equation of state, that is Pv is equal to mRT, which is mass inducted and delivered per cycle. So, you know m. So, for a reversible polytropic compression equation, we say Pv to the power n is equal to constant. So, that we can write P1 B1 to the power n is equal to P2 B to the power n. Now, from this PV diagram, what we can see is that work done per cycle is nothing but area A, B, C, D, and this area is nothing but area A, B, E, F plus area B, C, O, E and minus area A, D, O, F. Now, this area is very easy to, and most of the diagram they are rectangle, and other areas we can find out from this thermodynamic equations Pv to the power n is equal to constant. So, if you put that, then we can actually indicated work done per cycle is nothing but the work input per cycle. So, ultimately when you simplify these equations, we will write that work done per cycle is equal to n by n minus 1 into P 2 into V b minus P 1 into V a. So, this is nothing but P 1 V a is equal to m r T 1, P 2 V b is equal to m r T 2. So, roughly speaking, that we can simply say that P 1 V 1 is equal to m r T 1, P 2 V 2 is equal to m r T 2. So, if you look at this particular equations, and finally, what we get is work input per cycle is only a function of the temperatures at which they are operating, and here the pressure is now immaterial here, but this temperature is also a function of pressure ratio. So, to find T 2 we also require the equations P 2 P 1 B 1 to the power n is equal to constant, and from this also you can get a delivery temperatures. So, these two equations are now backbone or very basics for the reciprocating compressors. Now, moving further, now come up with the expressions that indicated power, which is m r T 1 into n minus n 1 into T 2 by T 1 minus 1, and putting this T 2 by T 1 as a function of P 2 by P 1, because many a times pressures are measurable quantity. So, you can write P 2 by P 1. So, the working equation for a compressor now becomes is indicated power I p is equal to m dot r T 1 into n minus 1 into P 2 by P 1 to the power n divided by n minus 1 minus 1. Many times we do not know mass flow rate. So, because most of the situations and mainly when you have incompressible nature, volume flow rate is a typical way of expressing this mass of the gas. So, we can represent in terms of volume flow rate. So, volume m dot r T 1 that can be replaced with initial pressure into this volume flow rate. So, this is how indicated power has two version of the equation, basically three version in terms of temperature ratio, in terms of pressure ratio, and both are in the form of mass flow rate. Another version of equation is that in pressure ratio and in the form of volume flow rate. So, these basic equations are very vital for a study of compressor. Now, once you know the indicated power, there is also possibilities that the actual power input to the compressor is larger than that of indicated power, just to overcome the losses due to friction. So, we introduce a term what we call as a mechanical efficiency of the compressors, and that is nothing but the indicated power divided by the shaft power. And how this shaft power is calculated? The shaft power is calculated when we add indicated power to this friction power, we get the shaft power. That is what the mechanical efficiency is defined. Now, when you have shaft power, then actually how much power we are going to apply for running the compressors, that is given by efficiency of driving motor. So, actual power input power which is required is the shaft power divided by efficiency of driving motor. So, shaft power already computed, so you can find out the actual power input. So, through this process from the indicated power to this power input, there are two efficiency, one is mechanical efficiency, other is the efficiency of the driving motor. And in fact, this is a continuous process, and these efficiencies are also very vital to know the actual power that is required for to handle certain mass flow rate of air or volume flow rate of air for operating a given pressure ratio. Another important segment of this compression work is that conditions for minimum work. So, an ideal compressor is the one which consumes minimum work for a given pressure ratio. So, the work done on the gas is represented by the indicator diagram, and it is the minimum when area under the curve is minimum. So, mostly what happens for a compressor situations, the height of the diagram is fixed by the required pressure ratio. Height means if you look at this PV diagram, the height of this diagram is fixed by the pressure ratio in which we are handling. So, under these two pressure ratio, we need to fit a compression curve. Now, which is the best? Then length is limited by the cylinder volume. So, if you have a given size, that means we need to have fixed pressure and we have fixed size of the cylinder. So, that is limited. Now, under these things we have to fit a curve which is supposed to have a minimum area under it. So, this is possible only when if you can play with the index of compression, that is n. So, n is typically unknown quantities, and till this point of time if you look at the idyllic nature of the plot. So, we have three situations. One is state A where the compression has to start, and the location B, we have two locations, one is B, we have a B1 and B2. So, three locations, and these three locations are extreme locations. So, we can have a process like AB, we can have a process AB1, or we can have a process AB2, and all these processes is done for a given size of the cylinder or swept volume of the cylinder and for required pressure range P2 and P1. And what are these three curve indicates? Now, in one situation we assume that n is equal to 1. So, it is a Pb is equal to constant, which is nothing but an isothermal process. In other extremes we have Pb to the power k is equal to constant, where k is equal to gamma, and this gamma, and if you say Pb to the power gamma is equal to constant, then it is a isentropic process. Now, we will see that which is the, and if you look when doing this nature of the curve, we can see that only if the process is isothermal, the area under that curve will be minimum. Now, what happens to the it is a natural nature that when there is a compression, the temperature is going to increase, but when a temperature is going to increase and side by side the process needs to be isothermal. So, it is a hypothetical case. But the thermodynamic nature for the process that tells us that we need to have an isothermal process if the area under that curve is a minimum. So, there are two extremes, isothermal and isentropic processes. Now, what we can see is that if you try to recall this diagram in a TS plot, and isothermal process will have there are two pressure ratios P1, P2, and isothermal process will take you in a straight line which is parallel to entropy axis, and another straight line would be 1 2 dash, which is just a vertical which is parallel to the temperature axis, and this is an isentropic process, and somewhere another process will be 1 2 which is in the medium in the somewhere in between, and that is the reason we have put n here. So, we cannot have isothermal process, even we cannot have isentropic process. Isentropic process means area will be the highest. So, isothermal compression is the most desirable process between A and B, giving rise to minimum work done on the gas. So, it means that actual compression process must have gas temperature as close to the initial temperatures. So, that means after compression you have to keep on continuously cooling, that is what I told, that when the compression is normally done side by side, cooling is provided, so that to the best possible extent we do not rise the temperature after during compression. So, based on the minimum work in the indicator diagram, we can now fix the isothermal efficiency. So, this is what we have summarized, is that we have now two works which is indicated work. One is a non-isothermal process which we have already derived this expressions. Other way is that we can find out the same expressions, that is indicated power for an isothermal process, and for an isothermal process we can write this P v is equal to constant. So, P 1 V 1 is equal to P 2 V 2 is equal to constant. Also, we have P 1 V 1 is equal to R T 1 and P 2 V 2 is equal to R T 2. So, accordingly based on these equations, if you can start from the basic principle, you can find out indicated work per cycle. We can write in the form that P m R T 1 ln P 2 by P 1. So, this is how we get isothermal work, this is how we get non-isothermal work. So, ratio between these two, because isothermal work is the work input for the compression which is minimum, and indicated work is actual work. So, it is a ratio between these two will give you the isothermal efficiency. Another important point that I need to emphasize, that what is the value of n typically maintained for this. So, the least as I mentioned, the least desirable form of compressions in a reciprocating compressor is given by an isentropic process. So, till this point of time always we see that isentropic process is a reversible one, it is a unique way to give the to define the reference state of any given process, but here this is completely avoided when you deal with the reciprocating compressors. So, isentropic process is the least desirable form of compression process, and in particular when you are looking at the reciprocating compressors. So, the actual form of compression is decided by two limits of index of compressions, and that is n is equal to 1 and n is equal to gamma, n for isothermal, gamma is equal to 1.4, that is for isentropic, and this is for air. Now, when we are dealing with air compressors, so we have to keep normally a intermediate number n which is kept in the range of 1.2 and 1.3. And another way of conclusion that we draw is that if you want to minimize the work input, then we must provide continuous cooling. So, the main method of the cooling of air is by water jackets surrounding the cylinder with best ratio of surface area to volume of the cylinder. Now, the last segment of our discussion in our course is that steady flow analysis. So, in one way that we have discussed about what is the power requirement for the compressors, And we say that when you deal with the compressor, that was a situation where we dealt with a non-steady system, it is a closed system type. Now, we can do another modeling in which we can work on a steady flow analysis. So, what does this mean? That if you can think that a compressor is a device in which there is some slug of gas at pressure P 1, volume V 1 and T 1 that enters, and it goes out at different states P 2, V 2, T 2. So, obviously, P 2 is higher than P 1 and temperature is also higher than T 1, and this compression process goes from 1 to 2 when it goes from state A to B or P A to P B it goes. Okay. Now, what happens in this process? If you say it is a steady flow, it can undergo heat interaction and work interactions. So, this is your problem, how you are going to deal with. So, in a steady flow analysis, we think the compression process is one of the steady flow with change of state from 1 to 2 and which is achieved by a non-flow polytropic compression. The steady flow energy equations for the systems can be considered for the unit mass flow rate by neglecting changes in the potential and kinetic energies. Now, also it is assumed that no heat is transferred on the introduction or delivery, but heat transfer can take place during the polytropic or non-flow compression process. So, that means this heat is getting transferred only during the process 1 to 2. So, none other way that it can go in, only during this process 1 to 2. So, if you can recall our steady flow energy equation again from the first law for open system, when by neglecting kinetic and energy and potential energy, we can write q plus w is equal to h 2 minus h 1, and here for an element process dq is equal plus dw is equal to dh. Now, if you recall that what is h is nothing but u plus pv, that is enthalpy is equal to internal energy plus flow work, and also from this we can write now dq is equal to du plus pdv, because when you put dh is equal to this, then we can have dq is equal to du plus pdv. Now, by putting these equations, ultimately we can now rewrite the fact that we can equate these two, and this pdv gets cancelled and du also gets cancelled. So, we can write dw is equal to vdp. Okay. And from this we can integrate w is equal to vdp, that is area A 2 vdp means area 1 2 B A 1. So, this is the area under which we are going to play to calculate this work, and from this we can now write what is V. V is nothing but P V to the power n is equal to constants. So, V we can write V is equal in terms of C and P, and from this we can integrate these equations, and finally, we can land up the same expressions, that is W is equal to n by n minus 1 into P 2 V 2 minus P 1 V 1 or is equal to n r T 2 minus T 1 divided by n minus 1. Here we are using these things, but the entire philosophy is that at the end of our analysis, we again come back to the same virtual expressions, that is W as a function of pressures as well as temperatures, and we also get the equations, that is work required for the compression, and in more or less the equation remains same, but our approach was different. So, there in the first case it was a closed system approach, and in the second case we have a steady flow systems. But at the end of the day, what the main requirement is that we have to find the work input for the compressors, and this work input is normally represented, or we call in this compressor term as the indicated power, and we call this, and this is calculated per cycle. If there are n number of cycles, accordingly volume will change. So, this is all about the entire contents for this lecture today. Now, we will try to solve a numerical problems based on the discussions what we have done today. So, the question that was given, that we have a single stage reciprocating compressors it receives 1.2 meter cube of air per minute at atmospheric conditions. That means, atmospheric air enters to the compressors at a flow rate of 1.2 meter cube, and the pressure ratio is 7.5. That means, the pressure is increased 7.5 than the atmospheric pressures, and for which the index of compression is 1.3. That means, here we have given n is equal to 1.3. So, we have to calculate the following indicated power, and if the compressor is driven by 300 revolution per minute, we have to find the size of the cylinder bore. Third thing, we have to calculate the power required for the motor, and fourth is isothermal efficiency. So, let us try to solve this problem. So, when you deal this compression problem, the first thing you have to show is that what is this thermodynamic processes that is involved here. So, first we have to draw the P V diagram, and the process we have to represent as 1 to 2, and this is P V to the power n is equal to constants. So, here given n is equal to 1.3, and here it is air. So, we require for air R is equal to 287 joule per kg Kelvin, and remember here n is not equal to gamma, even though you say air, but n you are taking 1.3. Then we have pressure, which is 1 atmosphere. This 1 atmosphere is nothing but 1.013 into 10 to the power 5 Newton per meter square, and we have temperatures. Temperature T1 we can assume to be 25 degree centigrades, that is 298 Kelvin. So, this is the things that we require the informations, and we also have P2 by P1 ratio as 7.5 and V1 which is given as 1.2 meter cube per minute. So, now we have to calculate. So, first question, that is we have to find the indicated power. So, if you recall this indicated power equation, I P is equal to n by n minus 1 m dot r into T 2 minus T 1. So, T 2 by first thing we have to find T 2 by T 1. Say T 2 by T 1 is can write it as P 2 by P 1 to the power n minus 1 by n. So, that means T 2 by T 1 7.5 to the power 0.3 by 1.3. Now, putting T 1 is 298. So, we can get T 2 as 474 Kelvin. Then we have to find out the mass flow rate. So, for mass flow rate we have to write m dot is equal to equation of state, that is P P1 V1 by R T1. So, P1 is given 1.013 into 10 to the power 5, V1 is 1.2, of course, you have to divide it by 60, then R is 287 and T1 is 298. So, we can find m dot is equal to 0.024 kg per second. Now, once you put this, then we can write I P is equal to n is 1.3 by 1.3 minus 1, m dot is 0.024, R is 287, T 2 minus T 1 is 474 minus 298. So, we can calculate now I P is equal to 5253 watt or IP is equal to 5.253 kilowatt. So, this is the first part. Now, moving to the second part. Second part is required, we have to find the compressor is driven at 300 revolution per minute. So, then we have to find out what is volume drawn into the cylinder is equal to, that means per cycle you have flow rate is 1.2 meter cube and 300 revolution per minute. So, 300 revolution per minute. So, this will give you 0.00 meter cube, 4 meter cube. Okay. So, we get volume and we are given with stroke to bore ratio. So, stroke to bore ratio, that means L by D is equal to 1.4. So, you can write the volume of the cylinder pi by 4 D square L is equal to 0.004, and from this your L is equal to 1.4 D. So, you can write this equation as pi by 4 D square into 1.4 D is equal to 0.004. So, this will give you dq is equal to 0.00363 and D is equal to 0.15 meter. When you have D is equal to 1.5 meter, L will be 0.21 meter. So, the question was that what is the length of the bore? So, it is 0.21 meter. Third question is power driven by the motor to drive the compressor. So, what we can write now is what is P in is nothing but indicated power divided by mechanical efficiency. Indicated power divided mechanical efficiency means we have calculated indicated power 5.253 divided by mechanical efficiency is 0.88 and this number is 5.97 kilowatt. And what is power required to drive the motor? P motor is equal to P in divided by transmission efficiency, that is eta T, and this is 5.97 divided by 0.92 is 6.5 kilowatt. And last is isothermal efficiency. I am leaving it to you. So, what we have to do? We have to calculate the isothermal work. So, that is for minimum work. So, we can have indicated power isothermal is equal to M R T1 ln P2 by P1, and isothermal efficiency will be now eta iso. So, we will have IP isothermal divided by IP, and this IP is already 5.253. So, the choice is with you, so we can find the isothermal efficiency by taking that ratio. So, with this I come to this end of this today's lecture. Thank you for your attention.